Yes. So in our chapter 2, so first unit, chapter 2, probability and information theory. Side. So here we have two different concepts. One is probability, another one is information theory. So under probability, we are learning random variables, probability distribution functions. So we are using distribution functions, that is measure one, and marginal probability, conditional probability, exception, variance and covariance, Bayes rule. These 6 topics I will refine, will do the revision under probability. So another one is information theory. Under information theory, we are learning numerical computations, overflow and underflow. This is related to little bit machine learning concepts. Overflow, underflow, gradient based optimization, constraint optimization, linear least squares. These 4 topics, or simply we can say 6 topics. These 6 topics we will learn here. These 6 topics we learn probability. Now, what is probability and why we are using probability? Simply, I can define a probability is one of the mathematical framework. So as we know that probability is one of the mathematical framework. So this mathematical framework we are using for resolving uncertainties. Okay, this probability represents uncertainty statements. Okay, so wherever we are having a situation, uncertainty situation, so this probability is responsible to deal with uncertainties. That means this probability provides a quantifying measure by deriving uncertainties. So we are resolving uncertainties. In artificial intelligence, the probability theory is defined in 2 different ways. So everything that we observe around us has some degree of uncertainty. So many times I am using word uncertainty because it has to register in your brains, then only you can understand probability. So what is this uncertainty? What is that uncertainty condition? So based on uncertainty, we are our probability is responsible to deal with uncertainties. For that, I will tell you with example in the next slide. So meanwhile, you just see here, all AI applications, the probability theory is used in 2 different ways. In entire artificial intelligence applications. So what is the artificial intelligence applications? That means machine learning and deep learning also part of artificial intelligence. So in all the cases, all AI, this is AI. So internal support is machine learning, internal support is deep learning. So all AI, deep learning, machine learning concepts which uses probability theory in 2 different ways. The first one is law of probability. First thing is law of probability. It specifies how artificial intelligence should be reasoned. That means one important application, probability theory application, is law of probability, which deals with a reason. What is the reason behind artificial intelligence system to implement this technique? So that deals with law of probability. Another one is use probability and statistics. It involves statistics, not only a probability, it involves statistics. So these 2 combination we are using to analyze a behavior of the proposed artificial intelligence system. Okay. To deal with the AI, we are using two different concepts of probability theory. One is law of probability. Law of probability means which is having all the properties, axioms. All these axioms are used to understand the reason behind intelligent thinking. Another one is probability and statistics. Whenever the word statistics involves, you can simply assume it defines some behavior of the proposed artificial intelligence system. These two things, that means reason, why we are thinking like this, that means artificial machine, why this artificial machine is thinking like this. For a reason, for understanding thinking capacity, thinking, that means measurement, assumption, we are using probability. Another one is behavior. Why it behaves like this? Why it responds like this? When we are giving input like this, why it generates this kind of output? That is decision. Output, based on the output, will make a decision. That decision making behavior is defined with the combination of probability and statistics. These two are essential things which we are using in our artificial intelligence applications. Here, artificial intelligence application means all. Then why? Why we are using this kind of probability theories? Two theories like probability specifications, law of probability, and probability with statistics. Why we are using these two? So because probability theory is a fundamental tool for any discipline. Like many disciplines which uses probability. For example, science. Science means mathematics is also comes under science. Physics, chemistry, that means all scientific science applications. There they are using probability theory, and also engineering applications. In engineering applications also we are using probability theory. So probability theory allows us to make uncertainty, that means uncertain statements, to make uncertain statements and the reason in the presence of uncertain. Why this uncertain is happen? We are identifying that state of the uncertainty. Okay. So information theory allows us quantifying how many students are joining. Okay. So I won't allow after 9:45 or 9:15. It is difficult to allow the candidate and taking the session. It's difficult. Okay. Right. So probability, which makes uncertain statements using law of probability, it makes uncertain statements. In the presence of uncertain statements, information theory allows to quantify the amount of uncertainty in probability distribution. So how much percentage is affected? The reason, behavior depends on the reason. How much percentage it is affected? That is also deals with the information theory. So combination of probability statistics and information theory together, it defines accuracy. It defines accuracy. That means precision. Final analysis will be defined. So that is the main reason we are using a probability. The probability theory allows us to make certain statements, uncertain statements, reasons, okay, presence of uncertainty, and information theory allows us quantify the amount of uncertainty in probability distribution. How much it is affected in the distribution, that is defined. I will explain what is uncertainty with example. See here, in day-to-day life, we are observing so many uncertainty statements. First one is when you consider first source, inherent stochasticity in the system being modeled. What is the meaning of this? Here, when we are defining interpretations, most of the interpretations of quantum mechanics that describes dynamics of subatomic probability. Okay, what is this one? It defines a randomness hypothetical statements. I think this terminology you are not able to understand, but I will tell you simple example with chord game. So when we are using chord game, okay, like a deck of cards, so we are randomly picking one of the chord. Okay, what we are assuming here, it is 1 second. 1 second, 1 second. Sorry. Sorry for the interruption. Okay. So instead of the statements directly from the probability, I will take one example like a card game. So when we are using hypothetical card game, like deck of cards, so that cards are well shuffled, and we are picking a randomly we are picking any one of the card. Okay, here our assumption is uncertain. Okay, what type of card we are picking is uncertainty. Okay, we don't know every time we are picking same card or not. But our hypothesis is every time uh, we are shuffling the cards and we are picking the uh, cards. So this is one kind of uncertainty situation. What type of card we are picking? Okay, so like that we'll define inherent stochasticity. Internally, it is having a randomness. Randomly, we are selecting the chord. So in our probability theory, it defines randomness. Okay, that is the major point. Randomness we are implementing here. Another example, when you consider incomplete observability. So in incomplete observability, so we can say that when we consider game example, see here, we have a puzzle. I mean, in your screen, you just see we have a puzzle. It is having 3 doors, door number 1, 2, and 3. So backside of this door, we have like a some object. Okay. So when we are opening the door, this object is appear any one of the door, that is sure. That means it is guaranteed that the object got here, the object will be appears any one of the door. So selecting that exact door, random selection is required. Okay, randomly we are selecting the door. So behind that door, it may be having that object, desired object. Okay, I'm not saying this is a particular animal or something. object. Okay, so our desired object is there in particular door number 1, so door number 2, or door number 3. So this is uncertainty. Okay, but we know that there is a object, our desired object, any one of the door. So this type of uncertainty, we can say it is an incomplete observability and incomplete modeling. So sometimes we may use incomplete modeling. So here the model which predicts, that means a mathematical model. This model predicts the object. So where this object is exactly similar to this example. Okay, so simply we will consider like a game. When we are opening a particular door or particular concept using our thinking skill, how we are assuming, how we are behaving with this object detection, the same way we are implementing uncertainty and also reason for this uncertainty along with the behavior. These three things will discuss in our probability. That is major importance of the probability. In entire probability, so we are dealing with two kind of probabilities which are directly related with each other. One is frequentist probability, another one is Bayesian probability. So what is this frequentist probability? This is a normal probability. Frequentist probability is a normal probability. Everywhere, every time we are using with randomness. Another probability is Bayesian probability. Here, the Bayesian probability which defines degree of belief. That means acceptance degree based on the conditions. Conditional probability, inherently we are using conditional probability, that is degree of belief will be implemented in our Bayesian probability. These two types of probabilities are there. We are using mostly in our machine learning, deep learning, we are using Bayesian probability instead of frequentist probability. What is this? This is a normal probability which is having sets, permutations, combinations, and other basic probability axioms. Whereas in Bayesian probability, it is having degree of belief that related, that means probability distribution functions we are using. Okay, so we are using in our deep learning programming or understanding of the deep learning concept with the probability distributions. Okay, so this type of probability we are using instead of frequentist probability. So to deal with the probability, we should know randomness. What is the randomness? Random variable. So in earlier examples, I am saying like randomly we are picking the code. Randomly we are selecting the object. Randomness. Okay. So that we need to understand in terms of random variables. What is a random variable? A random variable is a rule. Okay. So in our probability, a random variable is a rule which assigns a numerical value. What is the random variable? Random variable defines a rule, condition. Okay. Rule, which defines a rule. So based on the rule, we are assigning a numerical value. Numerical value means numbers like 0, 1, 2, 3, 0.5, 0.7, like number. Okay. So we are representing a numerical value. This numerical value should not be I mean, it is in two different categories again that we'll discuss later. You just remember a definition of a random variable. A random variable is a rule which assigns numerical value to each possible outcome. So whatever we are getting the outcome from the input, that means whatever we are getting output, this output should be a numeric value. Okay, this output should be a numerical value. This numerical value is assigned based on a rule. Okay, based on the condition or a property. So that property will defines our randomness. For example, when we are toss a coin, obviously when we toss a coin on sample space S, so it is having the output maybe either tail or head. Okay, so here in our random variables, randomness, so outcome should be in terms of number, numerics. That is, if it is head means we are represent that in terms of numeric value 1, it is tail means numeric value 0. So like this will assign a numerical value to this example, randomness. Okay, so we should represent this in terms of numerical values. This is the main definition behind random variables. Now you can easily understand what is a random variable. This is very important thing. We need to understand how we define random variables in our programming. Random variable is nothing but a rule. So based on the rule, we are deriving the output. That means assigning the output. This output should be a numerical value. This is a major definition. In our probability, the random variables are two categories. We have two types of random variables. Okay, so this random variable is maybe a discrete random variables or maybe a continuous random variables. Discrete random variable or a continuous random variable. What is the meaning of discrete and continuous random variables? In our first unit itself, we had a discussion about what is a discrete, what is a continuous. Our linear algebra follows continuous values. Okay, so but here in a probability, this probability is having discrete variables as well as continuous variables. These variables are random variables. Here, what is a random variable? These variables defines a rule. Based on the rule, the variable outcome will be defined. Okay. For that, we are using discrete or continuous random variables. First, we should understand what is the definition or meaning of discrete random variable and continuous random variable. Then only we can understand our concepts very clearly. Discrete random variable. So what is discrete random variable? A random variable is discrete if a value can assume isolated points on a number of lines. Okay. So when we consider a output like a lane, okay, in this lane, we are assuming the output will be isolated points. Okay. Isolated points. What is isolated points here? That means finite. Okay. Finite number. A discrete random variables are having finiteness. What is finiteness? Finiteness means we can count a particular thing. So output should be countable. Say for example, when we consider phone calls in a particular half an hour or particular hour. So our class is going on 9:40 to 10:20 or 10:30. So in between 9:40 to 10:30, how many calls you received? Okay. So in this example, how many calls you received? That is, we can simply count based on missed calls or received calls, like 1, 2, 3, or 7, 10 calls, 13 calls. That means this is finite number. Okay. Like that, we have a finite number counting. So that finite number, countable number, so we can say it is a discrete random variable. So when we consider another example, like you are doing a service. Okay, you are doing a job in service center. How many calls, service calls you have received in that particular day? Okay, or else vehicle service. When we are running a showroom, two-wheeler showroom or four-wheeler showroom, how many service vehicles are received in that particular date? So that should be a countable. In entire day, maybe 10 vehicles are serviced, 20 vehicles are serviced, 30 vehicles, or no vehicle is get serviced. So this type of counting the measure that will treated as discrete random variables in our probability. So that type of outcome will be defined in terms of number 10, 20, 30. That is a number. Okay. So this number is defined as an output. This type of countable things, we can call it as a discrete random variables. And comes into the continuous random variables. What is this continuous random variables? A random variable is continuous if its value can assume all points in particular interval. So all points are considered. This is one point, this is another point, this is another point, this is another point. So all these points are considered as an interval value. So then we can say that this variable is continuous random variable. So what is this continuous random variable? Simply continuous random variables which is having in terms of decimal values. Discrete random variables are simply numerical values which is not having decimals. But in continuous random variables, sometimes it is having a decimal value. That means we consider a range. Say, for example, this point is 10, this point is 11. Okay, so these 2 points should be in between 10 and 11, maybe 10.5, 10.7, 10.6, like this. Okay, so we can consider all the points together in our measurement. We can consider all the points together, then we can do our operations. This type of variables we are calling like a continuous random variables. In general example, height and weight of a student. Student height will be measured in terms of continuous random variables. 5 inches or else 160 centimeters, 170.1 centimeter. Like height will be measured in terms of continuous random variables in our probability. Weight value is also like 50.5 kgs, 49.6 kgs. Okay, some decimal value should be included, may be included in continuous random variables. Lifetime of a component. This is one more example. Or else we can consider response time. So when we are giving input to process, how much time it takes to process the result, generating the result, that time will be measured in terms of continuous random variables. Like 1 minute 60 seconds, 2 minutes 30 seconds. We are measuring like that time. And also we can consider price of a rent. Okay, price of a rent. All these things we can consider as a continuous random variables. So discrete random variables having finite and countably infinite. This is finite number of values in particular time slot, finite number, but infinite countable. So what is this finite and infinite? Sir, earlier you said the discrete random variables are finite. Say, for example, how many calls are received means it is a finite. Then infinite uncountable. Why we are adding this infinite uncountable means sometimes there is no limitation how many vehicles will be arrived in that particular day. How many calls you are receiving in that particular hour. It is infinite number. So you can receive n number of calls, but that is a finite. That n should be a finite number, but you doesn't know how many number of calls you are receiving. Okay, so 2 things are involved here. You should know in that particular hour you may receive 10 calls, 20 calls, 30 calls, 40 calls, 50 calls, 60 calls. Okay, so you cannot fix that boundary. That means you cannot fix how many numbers, but total count should be a fixed one. That is a finite one. Total count should be finite, but in that hour, we cannot predict how many calls we'll receive. So this thing is represent like a discrete random variables are finite or countably infinite number of variables. We are representing these variables with capital X, Okay, we are representing a capital X, and continuous random variables, which is having like a numerical value with decimal values. Okay, measurement will be in different things. So for doing these probability distributions base probability, we are using two different kind of distribution, two different kinds of probability distributions. One is probability distributions like a probability PDF or PM. PDF, that means probability distribution function. So, and another one is probability mass function. We will discuss these probability distribution function and probability mass functions in the next class. Okay, so you just try to understand the definition and the different types of random variables and why we are using probability. Okay, in today's class, we learn only three things. If you have any doubts related to basic definition of probability, you can raise your doubts.